So in this video, we're going to introduce and look at the periodic table. In the next one, we're going to move out of the history of the periodic table and actually get into the families of the periodic table, which will begin to introduce the topic for the following video, which is the patterns that are there in the periodic table. So let's start out with just some quick review. Of course, you just took a test over this, but atoms are the most fundamental unit of matter. They are made up of protons, neutrons, and electrons. And there are lots and lots and lots of atoms, of course, but there are only 118 or so different types of them. And those different types of elements, atoms, we call elements. Now, I say 118 or so. Right now we know of 118, but many of those are man-made, and we potentially could make more in the future. And there's room on the periodic table to continue the patterns, and we're pretty sure what they'll look like, those patterns at least, and can continue to add to the periodic table as necessary. Since I started teaching, we went from 111 up to 118, and we'd had a long period, a couple decades almost, of no new element discoveries. And so it's really been kind of fast-paced and exciting. I've got to see the naming of elements 112 through 118, their official discoveries being recognized, and then the naming of them occur. But depending on how you count, there's about 90 naturally occurring elements on Earth. All of them are below uranium on the periodic table. You'll notice uranium's number 92, which means there's two below uranium that aren't naturally occurring. Number 43, technetium, and promethium, which I think is number 61. And those naturally occurring elements combine with themselves, combine with other elements to form all of the matter that we see and observe. The periodic table is simply a chart that organizes the known and theorized elements. And I do want to emphasize that we usually call it the periodic table, but the proper term for it is the periodic table of the elements. Periodic table simply means repeating pattern table. And so we can have all sorts of tables filled with repeating patterns, but this table is the repeating pattern table of the elements. And so that is its technical full name, but of course everyone has shortened it to periodic table. And the version that you and I are used to really was only introduced in about the 1950s. And there are some who would love to make changes to it. Remind me later, and I will gladly show you my collection of periodic tables. I love collecting periodic tables, just pictures of them that I've saved on my computer, but I love looking at alternate ways that we could organize them, as well as fictitious periodic tables, which is a project that you'll be working on as well. And so there are different ways to organize the information on the periodic table, but there are certain patterns that we see in the periodic table. Anyway, if we go back far enough, we go back to ancient Greek times, and there were only viewed to be four elements: earth, air, fire, water, maybe a fifth one, spirit, but probably not. And those elements were viewed to combine in different ways or to have different levels of purity to make all the different substances. And in the 1700s, there began to be chemists, maybe very late 1600s, there began to be chemists who started noticing that there were different types of air, different types of gases is what we would call them now. And they ended up deciding that maybe it's not just air, and maybe these different metals aren't all just different levels of purity of Earth, with gold being the most pure. Maybe they are genuinely different elements, different substances in and of themselves. Antoine Lavoisier is considered by many to be the father of modern chemistry, and you'll hear his name come up again. But he has here his list of elements. This is one of the first list of elements, and you can see bismuth and fer for ferrous or ferric iron, mercury and nickel and lead here, and plum, and you can see his early list of elements. You can see, I think these are other names for the same things. And you can see here oxygen, which arguably he discovered first. There's a couple other claims for it, and hydrogen, which he did discover first, without a doubt. But he also has a mistake in here. You have lumiere, light, and caloric, heat. And of course, we know now that those are not elements. But the downside of just a list like this is that every time a new element is discovered, you have to reprint a list. Now, yes, you can add on to it, but there maybe is some organization here, and we certainly get into some organization here by apparent weight when we get to Dalton's list of elements in 1803. By that point, Lavoisier was dead. He was beheaded during the French Revolution, unfortunately, and so he was not able to advance chemistry as much as he would have wanted, as much as we would have loved him to be able to do. But anyway, here we have the Dalton's list of elements. And you can see here some of the old alchemical symbols kind of carrying over into modern times. But you can also see the starts of using letters to abbreviate and symbolize the different atoms. But again, this is just a list, and every time a new one was discovered, especially when you organize them by weight, you find a new one that has a weight that goes in here in between iron and zinc, and you've got to rearrange the whole table. You'll notice he has some of these out of order with where we have them nowadays. And so it's a start, but it's still not much. And there were people who began to notice patterns, who began to try to organize periodic tables. And there are all sorts of failed periodic tables out there. And then comes Dmitry Mendeleev, the father of the periodic table, to save the day. Story goes that back in 1869, that was 151 years ago at the time I'm recording this. In fact, last year was celebrated as the International Year of the Periodic Table, and all sorts of awesome periodic table celebrations going on to honor the 150 years since Mendeleev had created this one. But the story goes that he was tired of having to have his students, he was a college professor, have his students repurchase a periodic table or have these poor periodic tables or a list of elements that they had to constantly make additions to. And so he wanted to come up with a better way. So Russia being very cold in the winter, he was snowed into a cabin for a weekend and took the known elements and the known properties of those elements and began to organize them on note cards and began to physically rearrange the note cards on the table or on the floor, trying to come up with a pattern. Where he differed from others, though, is that he not only used mass for organizing, and I did skip the line there. Our modern table is based off of his. You'll notice here in a moment that they look very different. You can see our periodic table in there. But the reason that his lasted, the reason that his had staying power was not only did he see those patterns in the properties of the elements, but he also left blanks for undiscovered elements. He had the foresight to think maybe we haven't discovered all of them yet. And if so, maybe the reason the pattern doesn't work or the pattern begins to break down here is because there's an element we haven't discovered. In fact, he accurately predicted properties of those undiscovered elements. There are some who will say then that he deserves credit for discovering those undiscovered elements. I would say discovery goes to the person who actually finds it. He, yes, successfully predicted them. He theorized their existence, and his predictions helped chemists know what to look for. Because now, instead of just accidentally stumbling across an element in their experiments, when you know that there's one that's going to behave similar to aluminum, you can start going to aluminum ores, and the same ores that give rise to aluminum might give rise to that missing element. And that's actually one of the ones that happened, which you'll see here in just a moment. And so his big insight was to leave gaps, and then all you had to do was fill in those gaps. And so his table had staying power, and he lived long enough to see the discovery of the electron and protons, but he honored Dalton so much that he thought there's no way that Dalton was wrong. Dalton said that everything's made up of atoms, there's not smaller pieces, and Mendeleev died not believing in the subatomic particles that had been discovered up to that point. But his periodic table had staying power, and he does have element 101 named after him now, mendelevium. Anyway, if you look here, you'll notice he has 8 columns, as he calls them, groups on the periodic table, and this looks very different than ours. Now, part of that is just because this is more like a basic data table, and if you imagine drawing a line here in between each of these and actually putting each of them in their own box instead of in this columned list, you could start to see, okay, there's a whole bunch of boxes here. And then from there, the other thing is these are wide rectangles, and most of the times when we draw the periodic table, we draw them in squares. nothing says we have to do them in squares. I've seen some absolutely awesome periodic tables that are where the symbols are not written inside squares, and even writing them inside other shapes like a hexagon allows you to do different arrangements of them, which is one of my favorite periodic tables, is a hexagonal spiral. But anyway, you can begin to see it there. But notice, we just go down this first column. We have H, Li, Na, K, Rb, Cs, hydrogen, lithium, sodium, potassium, rubidium, cesium. The numbers here would be their weights, their masses, which were known at the time. Now he also has here Cu, Ag, Au, copper, silver, and gold. And those are in our periodic table still. They're just in a different column together. There's a lot of places on his table here where he has two grouped together, and in modern times what we've done is we've taken those two groups and we've split them apart. Well, if you take his 8 groups here and you double all of them, that gets you up to 16 groups. It turns out that there's a little bit too much combined here, and so this one actually got split into 3 groups, and I think there's one in here that didn't get split at all, is where those numbers, or when it got split, it merged with another. And so then that gets you up to 17 of our groups. And then you'll notice if you look through here carefully, there's no noble gases. The first one wasn't discovered till the 1890s, and it was discovered before he passed away. And he quickly realized, oh, hey, this is just a whole nother group on the periodic table. So he added a whole nother column, and in fact, he did different versions of this. And his 5th periodic table doesn't look as much like this one, or even as much like our modern day one, but he continued to make improvements on it through his life. But this is really the one that lasted. But I want to point out some of these places here where he has these gaps. So right here, we have Al, aluminum, mass of 27. I think that's 27.3, maybe 27.8 there that he has. But then underneath that, he has a blank, and he predicts a mass of 68. And he wrote about this. He didn't just do the table. And he called this one Eka aluminum, which literally meant just underneath or below aluminum. And this one here, he called Eka silicon, underneath or below silicon. And it turns out that if you go look at the modern periodic table for those two, underneath aluminum, we now have an element that we call gallium, and its mass is 69.7. So he's a little low there, but still very close. And if we come here underneath silicon, we have an element with a mass of 72.6. And so he's spot on for his prediction of germanium there. And over again, this happened on his periodic table, where he made a prediction, and later on, those elements were discovered. And I think it's 2 underneath. When you had 2 blanks underneath, it was DVI, but he just named them after the elements above them, knowing that they would get real names later on. There are a few mistakes on here, a few places where organizing by mass is going to throw you off, and there are a few you'll notice here where he has question marks, where he's like, I put it here, but I'm not absolutely certain that it actually goes here. In fact, if I remember correctly, this one here, didymium, we ended up discovering was actually 2 different elements stuck together, and when we separated them out, we got praseodymium and neodymium. And so there are things that were unknown at the time as well, but for what was known at the time, this was absolutely phenomenal. And the big organizing principle that he has here is mass and how many oxygens or oxygens and hydrogens these things bonded to. And so he was able to come up with what is the precursor to our modern periodic table. And so I know it doesn't look a lot alike, but they are similar. And of course, now the modern periodic table is arranged by atomic number. There were a couple updates to Mendeleev's table that were made. One of them was, of course, Henry Moseley rearranging them by atomic number instead of by mass, once we discovered that the protons were a thing, and that, oh, hey, all these missing elements, that it wasn't so much by mass, wasn't the, it was a helpful predictor for figuring out what it was, where it was, but knowing how many protons it had made it even easier to find them, and more identifying of those elements. And so Moseley did that, and later on in the 1950s, Glenn T. Seaborg separated out the bottom 2 rows just because it began to get too crowded. And so these two rows really belong right here, and I'll actually show you that in the next video here. But they really belong right here, and if we're picky, lutetium, lawrencium actually go underneath scandium, yttrium, and this column here gets split. But it gets hard to print on a page, and so Seaborg said, you know what, let's just move those two rows underneath, and that's kind of where we got our modern periodic table. But it's not necessarily the only arrangement, it's just the simplest and most famous, and kind of based off of the first arrangement. There are other competing ones out there, but none of them have really shown themselves to be more powerful than this one, in both simplicity of being able to understand it, as well as complexity in being able to show certain patterns and properties of the elements. But anyway, we'll get into families the next time. So be sure, if you have any questions, that you let me know.